are skewed. And here's how it works. If the skewness statistic is 0 or pretty close to it, well, then the data are pretty symmetric. If you drew a histogram of albumin levels and the skewness value was 0, well, then the histogram would be a perfectly symmetric picture. The closer the skewness is to 0, the more symmetric the distribution of that variable. Now, the further away you get from 0, the more skewed the data are. Also, if the skewness statistic is positive, then you're talking about positively skewed or right skewed data. If the skewness statistic is negative, you're talking about negatively skewed or left skewed data. How do you know when the skewness statistic is close to 0, or meaning that it's symmetric or at least relatively symmetric? And how do you know when it's large enough in magnitude that the distribution can't be regarded as pretty symmetric anymore? Well, there are no hard and fast rules. My rule of thumb is that if the skewness statistic is between -1 and +1, right, if it's between -1 and +1, then we have no more than, say, just a mild level of skewness. Once it gets past, once the skewness statistic is less than -1 or greater than +1, we're talking about more than just a mild degree of skewness, and you might want to think about that. Alright, so that skewness statistic. Here I'd say albumin levels are pretty symmetric, since the skewness statistic is very close to 0. It's 0.23. Underneath the skewness statistic we have the uncorrected SS. That actually stands for uncorrected sum of squares, and look back to quiz 1 when you get it to figure that out. Oh, that's not right. The uncorrected sum of squares was not on quiz 1. The uncorrected sum of squares is simply the sum of the squared albumin levels. So square every albumin level, add up all those squares, you get the uncorrected SS. Why do you need that? Well, you probably won't ever need that, but there is a formula which we've discussed in lectures where the sum of the squared variable values plays a role. Go back to the first few days of class and look at the lecture notes and look at one of the formulae for standard deviation or variance, and you'll see that the sum of the squared data values is used in that calculation. 3263.75 here. Apart from that, there's not much to say about it. Here's the coefficient of variation. It's 27.26%. Remember, that measures the standard deviation as a percentage of the mean, and I'd say 27% is a fairly high number. It could be higher, of course, but when the standard deviation is 27% of the mean, you've got a reasonably large amount of variation. The results are reasonably noisy, in other words, for albumin levels. It's not like you look at the mean and there's hardly any variation around it. There's a reasonable bit of variation in albumin levels around the mean. Okay, let's move on to the sum of the weights. This is not an interesting statistic for us. In fact, it's really just a sample size again, 377. In some types of studies, you can weight the different observations. This happens especially in some complex sample surveys that you might conduct, and well, we're not conducting any of those here, so really the sum of the weights is not necessary for us to worry about anymore. Our data are not weighted. Every observation has the same weight, a weight of 1, therefore the weights add up to 377. Alright, how about the next number, 107.0.3? That's the sum of the observations. You know what that is. You take all the albumin levels, you add them up. It's the numerator of the sample mean, if you wish. Then we've got the variance, 0.59887451, rounded I guess is 0.6. Well, that's just the square of the standard deviation. You know that. What's kurtosis? Well, we're going to talk about kurtosis a little bit more once we study the normal distributions, and we haven't quite gotten there yet, so I'm going to delay discussion of kurtosis. Not going to tell you what it is right now. Alright, here's the statistic that was on quiz 1 in lectures. The corrected sum of squares, that is the numerator of the sample variance. It's the numerator of the sample variance. That's all you need to know about it. In other words, it's the sum of the quantity x minus x bar squared values. The standard error of the mean we're going to talk about once we learn about hypothesis testing in a couple of weeks from now. SAS often is fairly redundant, or the SAS output has some redundancies in it. If you look at the next section of the output, you see the mean again, you see the standard deviation and variance again. You do see a few new statistics. So here's the median, 2.8. Here's the mode, 2.6. Here's the range, max minus min, 3.9. And here's the interquartile range. The 75th percentile minus the 25th percentile is 1.2. We're going to ignore this section called tests for location for now, because again, that has to do with hypothesis testing, which we will get to in a couple of weeks. Alright, what do we have next? We have selected percentiles which are presented. We've got the 100th percentile, the 99th percentile, 95th percentile, etc. For example, if you wanted to know what's the 95th percentile of albumin levels for this sample, it is right here. It's 4.1. Enough said about that. Let's finish off this output by looking at the very last piece. You have to scroll down to find it. And actually, I lied. There are two more pieces. There's the extreme observations table, which I believe I have pointed out to you before in demonstrations. This is useful because SAS shows you the five lowest albumin levels right here highlighted, and it shows you the 5 largest albumin levels. Often the most serious or the most gross typos in your data set will show up here. If somebody had typed in a 50 instead of 5.0 for somebody's albumin level, well, that would have shown up in one of the 5 largest observations, and so on and so forth. In my own work, I often, when I'm looking at proc univariate, I often come to this section first to make sure, to find those really grossly mistyped data values, because there's no sense really in looking at all the other statistics if you've got grossly mistyped values which you need to go back and correct. And by the way, notice that SAS not only tells you what those 5 smallest and 5 largest values are, for each value it tells you what the observation number is. So this 5.0, it occurred 3 times, and it was observations 9, 61, and 77 where the albumin level was highest. And so you might want to go back if you thought 5.0 was an unusual value and study the data records for observations 9, 61, and 77. Okay, here's the last section of the output. It's called missing values. SAS gives you a little summary of missing values. It tells you that missing values were represented as periods in the data set. That's pretty typical. SAS, by default, will represent missing values for numeric variables with a period. Remember that, okay? So the period, how many times did that occur for albumin levels? It occurred once. And since there were 378 observations altogether, including the missing value, that one observation makes up 0.26% of all the 378 observations. Okay? And this number is pretty silly. You can denote missing values with different symbols, and if there were different symbols, this last percentage would be telling you what percent of the missing values were periods, what percent of the missing values were, well, other symbols that you might use. We've only got periods here for missing values. That's the default anyway for SAS. And so 100% of the observations that were missing were represented with periods. Usually this last number is not all that useful. But it is interesting to know that we've got 0.26% of the observations missing for albumin. That's not a very high level of missingness. If there was a high level of missingness, well, I don't know what, 10%, 15%, 20%, now you start to worry that maybe your sample is really not representative because you've got such a high degree of missingness. That's not the case here, luckily. So there you go. We're done with this particular proc univariate output. Before I let you go in this recording, I know it's getting long, I want to do one more thing. In step 4, we're going to go back and rerun this proc univariate code, rerun it, adding a histogram. You know how to do that from the very first lab this semester. You basically add a histogram statement into the proc univariate code. So if you compare the previous step, step 3, with this step, it's very, very similar, except that we've added a histogram statement for albumin, and also we've added this plot option to proc univariate. These do 2 different things. The plot option will create a box plot and a stem and leaf plot, and the histogram statement, of course, will produce a histogram. Alright, I'm going to stop this recording here, and I'll have a part 2 coming up shortly.